I will be starting right now since we have just, we have gone 5 minutes. So my name is Jude and I'm a member of the CDM. And I'm not just here alone tonight, even though I will be moderating these. I'm happy to be joined by the communication director, who is Jen Hafanan, who will be advising me throughout, as well as our director and Wiping Zoo and the staff of CDM. I see Jack there, Julian Arino, Michael Lee, and the others. So I'm happy to be joined by them. They will be in the background. You might not hear them speaking, but they are here with us. And we are grateful that you took time to attend this second series. And one more thing that we are grateful with this second lecture series is that we have, guys, the president of the Canadian Applied and Industrial Mathematics Society with us opening this second series. How great is that? So this is something great. And there is another surprise that we have tonight. It's not just having the president with us. We equally have a great, I don't think I should say this right now, but I will say it soon. We have a great guest among us who would like to welcome us to the second series because of how important it is. And this guest, I cannot stress more about how important these guests have been to the Canadian Center for Disease Modeling. She has done all the best to see that the Canadian Center for Disease Modeling succeed. The Canadian Task Force for COVID-19, she gave us all the resources we needed to see that we are able to get this monster off this country and the whole world at large. And that person is no other person than our Associate Dean, Jennifer Steele. So she'll be joining us tonight to welcome all of you, to show how much we appreciate your presence with us tonight. Without further ado, because of the time limit, I will welcome our Associate Dean to welcome all of you, to show how much we appreciate your presence here with us today, and how we appreciate that you bring your efforts together so that we get rid of this monster. Jennifer, you have the floor. Please clap for our Associate Dean as she takes over the floor.
Well, thank you so much, Jude, for your kind words. I must say that I'm really pleased to be representing the Dean's Office at York University this morning. And Jude, truly it is very easy to support all of our wonderful mathematicians here at York University because you really are a fabulous group. So this morning, thank you so much for inviting me to welcome everyone, and what a fabulous group. I can't believe how many, I'm scrolling through the pages and pages of attendees here today. This is just wonderful, and everyone is from across Canada and around the world. This is great, and I'm actually zooming in from Hamilton today. My daughter is at McMaster University, so I'm spending a few days with her. So this is kind of nice, actually. Zoom is allowing us to do different things that we wouldn't be able to do if we were in person. So I am very pleased to help launch the Canadian Centre for Disease Modeling second Distinguished Lecture Series on modeling and control of infectious diseases. And as everyone knows, this topic couldn't be more relevant and more urgent today across Canada and around the world. And we are truly so fortunate to have so many leaders in the field here at York University and across Canada. And I'm sure that Jude will be doing a welcome of the first speaker of the series, who is Dr. Rebecca Tyson from UBC Okanagan. And as Jude said, she is also president of the Canadian Applied and Industrial Mathematics Society. And her talk is on COVID-19, opinion dynamics and economics. I am really interested in learning more about this, and I'm thrilled that you're recording this, Jude, because I'm double booked, but I will be looking for the recording of this after the lecture. So I will hand it over to you, Jude, and welcome to everyone for this important distinguished lecture series. Thank you so much.
Thank you very much, Jennifer, and thank you all for coming. Jennifer, thanks so much for welcoming our guests. It shows how much importance Canada as a whole and York University placed on this Canadian Center for Disease Modeling, how much importance they placed in us using our models to see that we get rid of the monster. And I really appreciate that, Jennifer. As Jennifer mentioned, we are pleased to be joined today by the president of the Canadian Applied and Industrial Mathematics, Professor Rebecca Tyson, who is a professor in the University of British Columbia, Okanagan in Kelowna, British Columbia. Her work lies mainly in the area of theoretical ecology, specifically population dynamics and dispersal of populations in variables landscapes. She has worked on questions related to predator-prey cycles, mountain pine beetle dispersal, pollination services of honeybees, and human-bee interactions in interface communities like Western Bees, British Columbia. The model that she uses include ordinary differential equations, partial differential equation, as well as individual-based computational models. Recently, she has become interested in dynamical interface between ecology and humans' opinions. This is really important given human opinions on quarantine, as the latter is a critical component of the conservation work in the former. The ecological opinion dynamics interface is closely linked to the epidemiological/opinion dynamics interface. And so this second interface has emerged as an important trait in Dr. Tyson's work. Please welcome Dr. Tyson.
Thank you very much, Jude and Jennifer, and thank you everyone for coming. One small correction, I'm actually president-elect of CAMES, so Thomas Hillen is the current president and I take over in June. So I'm still in training at the moment. hope to be doing a good job when that starts next June. I can share my screen now, Jude?
Yes, please do. Thank you so much. And while Jennifer is speaking, please, may I remind you to type your question on the chat. And if you would like to come on and ask your question directly when she's done, please let us know. Just send us a message on chat privately to me or Mike, one of the greatest postdoc that we have, Elena Arufo, and she will be able to bring you on.
Okay, so can you see my opening slide?
Yes, we can see that. Thank you.
Okay, great. All right. So I promised to talk about economics as well. I don't know if we'll get that far. For starters, I want to focus on the opinion dynamics part of my work because that is, I haven't seen much work on opinion dynamics in disease, though as COVID progresses through the world and we see how it behaves differently in different countries, I think we're all beginning to realize just what a big role opinion dynamics has in diseases like this. The photo there is taken from Okanagan Mountain Park, just south of the city of Kelowna. Essentially, you can bike there if you're willing to bike far enough, and it's a beautiful place. So I do invite you to come and visit anytime if you're able. This is work that has been ongoing for several years with two collaborators here, Steve Crone in the middle and Bert Baumgartner. Steve Crone is a probabilist and Bert is a philosopher, and the two of them are at the University of Idaho in Moscow, Idaho. What happened with this project is that I asked Steve a question one day. I said, you know, what proportion of the population do we need to have on board before we can actually have action on climate change? And the reason I asked this question is because I had read that when you are a minority, you don't have to get to 50% of the population to stop feeling like a minority. Somewhere around 30% is enough. And so I wondered what the tipping point was for climate change. And so we started thinking about that question and realized right away that we couldn't answer it until we'd understood how opinions evolve in a population first. So that's where all of this started. And Bert, being a philosopher, knows quite a bit about how opinions evolve in a population and what the theories are for those processes. And so this has been a very fruitful collaboration. A couple of students worked with me too. I don't know what this yellow thing is. Are you seeing it on the screen, Jude?
No, there's no
Okay,
yellow.
good.
Yeah, this is good.
Okay,
Yeah.
there's something funny on my computer, whatever, as long as it's local. So these are two students who were undergraduates at the time that they worked with me, Noah Marshall and Stephanie Hamilton. Noah is now doing graduate work at McGill, and Stephanie is doing graduate work at UBC Okanagan. And they both have been instrumental. And then up front, I just want to thank my funding sources, NSERC, and then I'm part of the UBC Okanagan Institute for Biodiversity, Resilience, and Ecosystem Services. And that has been a wonderful group as well. And I've, through the talk, I couldn't resist adding a few photos. Because of COVID and everything being online, I was able to drive to Ottawa and visit my parents, and we drove back just last week during peak color. It was amazing. I haven't seen it in years, so it was a real treat. All right, so for the opinion dynamics and disease dynamics, these are the main questions we were thinking about. So how do opinions evolve in a population? How is the outcome of that evolution altered if different subgroups are more influential, or if there's more or less mixing in a population? And then if we couple that with disease, I really wanted to get to the climate change question, but disease is easier. So this is where we started. Then we can ask questions, how do opinion dynamics alter the time course of an epidemic? And how is the outcome altered if the opinion dynamics are faster than the disease dynamics, or if the population is polarized? So the outline of my talk is I'm going to start with voter models, which are the background to a lot of this opinion dynamics work. Then I'll introduce our model for opinion dynamics and some of the results answering my first group of questions, and then look at the coupled opinion dynamics, disease dynamics model. So the basic voter model it involves a population with two opinions. We'll call them purple and red in my figure here. The simplest one is just a line or even a circle of opinions. I've got a two-dimensional lattice here, which is one of the simpler versions. And the way the basic voter model works is that a focal individual is chosen, and an individual for that person to interact with. So my focal individual here is this red individual, and at random, the red individual chose this neighbor, which happens to have a purple opinion. And according to the voter model, the focal individual adopts the opinion of the randomly chosen neighbor. So the randomly chosen neighbor here is purple. So the red opinion is going to become purple. And now we have our new distribution of opinions in the population. And this process repeats. So we have another randomly chosen pair. These two had the same opinions already, and so there's no change. We could choose another pair at random. This time, because I'm telling you this, the focal individual is the purple one, and the red individual is the one being interacted with. And so the purple individual becomes red. And in this way, the opinions in the population are updated over time. There are many variants to this model, many variants. One of the simpler ones is the threshold voter model, where now our focal individual looks at all of its neighbors, not just a single one chosen randomly. And then looking at all of those neighbors, takes the majority opinion. And you can set the threshold at different levels. For the illustration here, I've just said the majority. So as long as at least 4 of the neighbors have a different opinion, the focal individual will adopt the other opinion. But you could set a threshold where a higher number is required. So you could say at least 5. So if I said at least 5 needed to be of the opposite opinion before switching happened, then it would delay switching. In this case, I've said 4, and so this focal individual is going to become purple, and there's our new distribution. So people ask all sorts of questions using these models. Physicists have been interested in them for a long time. And you can, especially with this lattice model, you can do a lot of mathematics, and you can ask questions about consensus. Is consensus going to be reached, and how long will it take? Yeah?
Can you use this full screen view? A lot of viewers are asking if you could use the full screen view.
I am on full screen view, so I'm not sure how to fix that. Okay, wait, but I put it in full screen after I shared. So how about maybe I stop sharing and then I share again and it'll work?
That could help. Just try to see. Okay.
Yeah, I'll try that. So there's stop, and then I'll share again. And is that better?
Let me see. From my side, it was good the way it was, but just see people asking. Let me see. I think it's better.
Yeah, now it's full screen.
Now it's full screen.
Okay, I'm sorry. Okay, so for the basic voter model, it turns out that consensus will not be reached in infinite time or on an infinite lattice if the dimension is too large. So if the dimension's small, you'll get consensus. If the dimension's large, then you won't. On a finite lattice, you always get consensus eventually, because once you lose all of the dots of a particular color, you can't ever get them back again. So, so you can get to consensus, but it can take a really, really long time. And then these variants on the model will affect the time it takes to reach consensus. It will also affect the structures that appear in the model. Do you get clustering or not? And how do these clusters change shape and move in the population? If you're interested, there's quite a bit one can read about voter models. This particular review is a really good one by Castellano, Fortunato, and Loreto. And it gives some of the physics applications of the model. And then while I was preparing this talk, I just came across this paper. The voter model is generally thought of as a fairly theoretical representation of opinions and is not generally applied to real data, but someone recently has done so and found it to be useful. So that's where we started from, but we wanted to build an opinion dynamics model that was a little more sophisticated. This is a picture from 2016, from Elections Canada. Here are the poll results for the Liberals, the Conservatives, the NDP, the Greens, and the PCC. And you can see that opinions are evolving. So something interesting is happening. And we'd like to try and understand some of this behavior. So we assume in our model that people are having meaningful interactions. So there are lots of interactions that are not meaningful, that aren't going to result in any sort of change of opinion. We're just modeling the meaningful interactions where people take some time to talk and understand each other's point of view and could potentially change their position. We assume that each individual has an attitude from the attitude spectrum that goes from -L to +L, skipping over 0. We had trouble figuring out how to deal with 0. So you have to have an opinion of some sort, even if it's not a very strong one. So the voter model that I showed you, there's either a yes or no or a 1, -1. We actually allowed a larger spectrum. So you can hold your opinion very strongly if you're at either the positive or negative end, or you can hold it very weakly if you're at the near 0. So given a particular attitude, small a, then the sign of that attitude is the opinion, and the strength of the opinion is the absolute value. Now, having defined that, I should use the word attitude a lot, and I tend to use the word opinion and attitude interchangeably, so forgive me if I do that. Anyway, so we have attitudes that go from -L through opinions on the minus side up to -1, and then skip over to opinions on the other side, +1, all the way to +L. And then updating of opinions in the model is not simply going to be, you know, random choice of neighbors or, you know, taking the average. We're also going to include a concept that we call influence, another concept called amplification, and a little later we will look at mixing. So I'll start with influence and amplification and then go to mixing. So influence, we assume that the likelihood of an individual's opinion affecting others depends on the strength of that opinion by an influence function. Okay, so what do I mean by that? Some possibilities are that all attitudes have the same weight. So if you're in a meaningful discussion with another attitude, it doesn't matter how strong that attitude is or which side of the opinion divide it's on, the weight is the same. On the other hand, we might assume that extreme attitudes have more weight, they're more persuasive. Or we could assume that moderate attitudes are more persuasive. So we call these uniform influence, linear influence, and collinear influence. We also looked at quadratic and co-quadratic influences. But to keep things simple, I just want to talk about these three. Amplification is a concept that comes out of the research on opinions. It has been shown that if you take two people who have the same opinion, but different attitudes, so maybe one of them's a +1 and the other one's a +2, if you put them alone in a room and give them time to talk about the topic, they will both come out more convinced that they're right. And so then the +1 might move up to a +2, and the +2 might move up to a +3, without the presence of any stronger opinions being there. Just the fact that the two of them are on the same side results in this amplification process where they become more entrenched. So how does this work mathematically? So if my purple individual is the focal individual, and my green individual is the one the purple one is going to interact with. Without amplification, we're going to assume that the focal individual moves towards the other individual. So as long as this green individual is somewhere up to the left of my focal individual is going to move one step to the left after that interaction, without amplification. With amplification, notice that the green and purple individuals are both on the plus side of the spectrum. So this purple individual, after interacting with the green one, is going to be more convinced of his or her opinion and will move one step to the right. So amplification will make the opinion become stronger, and without amplification, we get this centering tendency where opinions move toward each other. Okay, I hope that's clear. Are there any questions about that? Okay. All right. So now the basic model has no mixing. So if we implement this in an agent-based model, which is a little like the voter model lattice I showed you, we obtain these results. So I think this is a -5 to -5 spectrum. So these bars here are a histogram of the opinions in the population. So we've gone from -5 to +5 here. And we have a fairly uniform distribution of all the opinions. Now, if we let the system evolve, the first thing that happens is we get this centering tendency. And then it flattens out. I'm just going to focus on the distributions for now. We'll talk about the pictures in a moment. Spreads out, and we start seeing two peaks develop. And eventually we get this bathtub distribution where we now have polarization because we've got peoples mostly distributed at one extreme or the other. And this bathtub gets more, the polarization becomes more and more strong over time. We find that we do get consensus eventually, but it can take an enormously long time, especially if a structure like this develops. So in a square lattice, if you get either a vertical or horizontal cluster, then it can take an extraordinarily long time. And you can actually get stuck if it becomes perfect. Okay, so looking at the spatial distribution of individuals, we see first we have a nice mix, and then we start seeing these clusters developing, and then the clusters become more and more distinct, and they start swallowing up other clusters. So this one's gone between these two pictures. It's become white, and some of these individuals have become black. And then we get this, here's the polarization. We see more black and more white, and the difference between the two, there's less and less gray. Okay, so this is what happens with a little bit of amplification. If you don't have amplification, here are plots of these processes of centering, polarization, and consensus. What we've plotted here is orange is the centrist opinions, and then green and blue are the extreme opinions on the left and the right. Don't worry about fizz. Fizz is essentially a notation. Everybody goes to the center, and the extreme opinions disappear. With a little bit of amplification right away, so we have centering to start with, so the centrist, the number in the center opinions increase, but then start to decrease as the extremes begin to take over. And then you increase amplification, then this pattern happens faster. So now there's less centering. It always occurs, there's a little bit at the beginning, but there's less of it, and the polarization is happening more quickly. And then as we don't see consensus happening in these yet, because consensus is very slow in this system, but we can see that one side is starting to win out. And if we wait long enough, then one will win. Now, I talked about these influence functions. So who has influence? Do you listen to the people with strong opinions, or do you listen to the people with moderate opinions? So this is listening to the people with strong opinions example, and here's one of listening to the people with moderate opinions. All the other parameters are the same. And so listening to the extremes makes this polarization happen faster, and the loss of one extreme is actually happening faster as well. If the listening is to the moderates, then the centering lasts much, much longer. Okay, so we find that a little bit of amplification, or it can be a very small amount, and then giving weight to extreme opinions, either or both of these, will lead to polarization in the population. Consensus is very slow. And if co-influence, so a stronger influence of moderate opinions, can counteract the polarizing effect of amplification if amplification is low enough. Okay, now, so what if we add mixing? So then we want to look at an ODE. If we let X be the global frequency of attitude A at time t, and PA be the fraction of interactions that result in amplification. And then we define a variable omega, which is the frequency-dependent weight of attitude A at time t. And here's the definition. So we take the influence of that attitude and divide it by the influence of all the other attitudes, or all of the attitudes, including this one, multiplied by their representation in the population. Okay, so then we write the ODE, we simply write down our compartments. We've got our -2, and we're going to do the case L equals 2 because that's simpler. So we have a -2, -1, 1, and +2 group, and we keep track of the movement from one group to another. So the change in -2 population, so that population increases if a -1 becomes a -2. So these are all the interactions of the -1 that lead to it becoming a -2. Sorry about this parenthesis, that shouldn't be there. So if a -1 interacts with a -2, this is the weight, so the rate at which those interactions occur, then a new -2 individual is created. If a -1 interacts with a -1, and this is the frequency with which those interactions occur, then if amplification is present, that -1 interaction leads to a -2. So that's an example of how we built the model. These are the interactions where we lose -2 individuals and they become -1s. And so if we work through all the compartments that way, we arrive at this model. It looks complicated, but it's simply an accounting of the movement from the different populations or opinions. Okay, so we require the sum of all of these subpopulations to be 1. And so when we have that constraint, we have 3 steady states. The first one is everybody consensus on -2. The second one is everybody consensus on +2. And this is an intermediate where we have opinions across the spectrum. Now, it turns out if you do a stability analysis, you don't learn much because all of them are saddle nodes. So we run a bunch of simulations starting from a uniform distribution. And we see, as we did with the spatial simulations, we see this centering initially. So the yellow and the cyan here, these are the center opinions, -1 and +1. And then the blue and the red, these are the extreme opinions. And so initially, the extreme opinions are heading to 0, and the center opinions are increasing. And then we see at some point there is a breaking of that symmetry. And if we look here, the yellow and red, those are +2 and +1. And so the opinions on one side go to 0, and the opinions on the other side win out. So this suggested that we might be able to simplify the model in order to try and understand what's going on. Oops. So our first simplification is to assume that the inner opinions are doing the same thing and the outer opinions are doing the same thing. So if we let little x be the inner opinions, little y be the outer opinions, then we arrive at this two-dimensional system for the model. And we know that x plus y should add to a half. So that's this line here. This is x plus y equals a half. And then we're going to plot the inner opinions on the horizontal axis and the outer opinions on the vertical axis. And this is the steady state. And we're starting at a uniform distribution. So that's at both around a quarter. It's around here. And we can see from the phase plane that the system is going to move along this line toward the steady state. And in fact, if there's no amplification, this line here is the stable manifold for that saddle. When there's a little amplification present, it shifts a bit. Anyway, the system will move towards the steady state, but eventually will fall off. And so then we have trajectories that move to the right or to the left very, very quickly. Now these are non-physical because we need the system to remain, the sum of those opinions to remain a half. So this is the symmetry breaking part. of the system, where now what happens with symmetry breaking is that one of the inner opinions is increasing really, really quickly, and the outer opinions are near zero. Okay, so the second simplification is to assume that the opinions on one side have gone, they're zero, and we have little x inner opinion on the other side and little y extreme opinion on the other side. So now x plus y needs to add up to 1. This is our new model. And the constraint line is here. So this is x plus y equals 1. Now we were starting after symmetry breaking. We saw that one inner opinion was becoming large, and the outer opinion was low. So we're starting somewhere here. And then we can see from the phase plane that movement is going to be towards this steady state here, which is close to consensus on one of the outer opinions. So this explains the behavior of the full four-dimensional system. And not surprisingly, if you add enough mixing to the agent-based model, then you can find a match between the predictions of the ODE and the agent-based model. All right, so having understood opinion dynamics, we'd like to couple these with disease dynamics. So, and in fact, when we did this work, it was a good start. We started this 2 years ago. We were thinking about SARS, and then a month after we published the paper, COVID came along. So it was surprisingly relevant. But we had essentially the COVID setup, where now we've got an attitude +2 with no prophylaxis, -2 is high prophylaxis, and +1 and -1 are in between. And we assume that attitude predicts behavior. So individuals in the +2 population are going to have the highest transmission weight. And then individuals in the other populations have their transmission rate discounted by this factor Q, Q squared, Q cubed, as prophylaxis increases. Okay, so the model structure then is we have the opinion dynamics as before, and now we've added an infectious and a removed group with transmission rates towards them. Influence this time is a little different. So in the absence of any infection, influence is constant. So we're assuming uniform influence. But once infection starts, now the influence of each group is going to change. So we have several different possibilities here. A linear influence that keeps increasing. So the dark, the bold curves are showing influence of the prophylactic group, and the thin curves are influence of the non-prophylactic group. And we have assumed throughout that the prophylactic individuals have more influence than the non-prophylactic. That may or may not be true in all scenarios, but this is what we assumed in our model. And then we have in all three of these cases, we've assumed that the most prophylactic individuals have the most influence as infection increases, except in this case where we've assumed that the more moderate opinion here has more influence than the extreme prophylaxis. Okay, I see that we're running we're quarter past here, so I'll try to move a little more quickly. So the model equations look the same as before. These are the opinion dynamics equations, where now omega, this frequency of interactions, is affected by the amount of infection that's present. And then we have the disease dynamics term here. So the new model is the old one with disease terms added and omega depending on infection. And this is what our simulations look like. So we're interested in how these different influence functions affect the rate at which the epidemic spreads. And we're also interested in the effect of the initial conditions. So I'm showing here what happens if a disease arrives in a novel disease arrives in a population that is not prepared for it. And so it's a non-prophylactic population. They weren't expecting a disease, and the epidemic happens. So black here is the infectious population. Purple is the final size. So this is the removed group. And we can see that these different influence functions do affect the final size. So our largest final size is with the linear influence function, and our smallest final size is with the reverse order saturating. I'm sorry, the grid didn't, I guess I scaled the image down too far, so you don't see the grid, but this is the smallest final size. And that's with, so a non-prophylactic majority, we've got 30% of the population is prophylactic, and close to 70% is non-prophylactic. If instead we start with a prophylactic majority, so this population was warned and knew that the disease was coming, the final size is much smaller, and the different influence functions don't make as much difference. The reverse order saturating and the fixed order saturating are both quite small. So if we look at the initial prophylactic distribution in greater detail and look at the final size, peak size, and duration of the epidemic, we find that the more prophylaxis there is present in the population at the beginning, the smaller the final size and the smaller the peak size. But the duration does the opposite. It goes up until we reach a point where the reproductive number is so low that the disease is unable to spread and the duration is very short. This is looking at the rates. So in the first row here, we've increased the rate of the opinion dynamics. And in the second row, we've increased the rate of the opinion dynamics and the disease dynamics. So if the opinion dynamics are faster, we have similar behavior to what we had up here. But now the spread between the different influence functions is much bigger. So it makes a much bigger difference who you listen to and who has influence in terms of final size and peak size. These are all of the saturating influence. This is linear, and this is no or just uniform influence. It doesn't change. And so all of the saturating ones behave about the same. The linear starts out looking like no influence, and then eventually, with enough prophylaxis, becomes like the saturating ones. Duration behaves the same way, but again, a larger difference. Now, if the disease and opinion dynamics are both faster, we can end up with some interesting behaviors where so final size is always decreasing with initial prophylaxis, but it levels off in this case. There's only so much you can do starting out with initial prophylaxis. And it's the listening to the extreme opinions becomes more important. And duration just increases for these parameters. Okay, so the other aspect of this problem that I've been really interested in recently is polarization, and asking how polarization affects final size, peak size, and duration. So we came up with this function to define polarization. Polarization is directly proportional to the proportion of the population at each extreme. And two, this is a measure of what the difference is between those two extremes. So do you have a 70-30 split on the extremes, or do you have a 50-50? So 50-50 is more polarized. This is the difference between the proportion in each extreme. So if that's 0, then this factor is 1, which is the largest it can be. So that would be a 50-50 split. If you have a 60-40, this difference becomes larger. We square it so it's positive, and then discount the 1 here by that difference. And so if we plot this function, we obtain the contours down here. So this is the proportion non-prophylactic, or the S +2 population, and this is the proportion prophylactic, or the S -2 population. And so highest polarization by this function is in the middle, when you've got 50-50. And then lower polarization is when you've got, you know, a 90-10 split. So it's still polarized because you've got opposite opinions, but the overwhelming majority are on one side. And so for any particular value of polarization, I can get that same polarization by distributing the population differently on the two sides. So in order to plot final size, epidemic, peak size, and duration, and figure out how polarization is affecting it, I'm going to need to distinguish the two sides of the curve, or the contour plots. So these red points here mean that the polarization is skewed towards the plus side, and the green, or toward the non-prophylactic side, and green means the polarization is skewed towards the prophylactic side. Okay, so then if we look at final size, the initial, the final size on average decreases with polarization, but is always longer if the polarization is skewed towards non-prophylaxis. Peak size, again, on average, decreases with polarization, but is always higher if the polarization is skewed towards non-prophylaxis. Duration is a little more complicated. Initially, so for low initial levels of polarization, non-prophylactic distributions have longer epidemics. But as polarization becomes high, now it's the prophylactic distributions that have longer epidemics. Okay, so what do we find? So this is a fairly simple model of opinion dynamics. And yet we find some very interesting behaviors. So first of all, we see that opinion dynamics can both dramatically reduce epidemic size and peak size, or they can make things much worse, depending on how the rates interact and what the initial distribution is, and how the population is mixing or not. The initial conditions are important, and that includes both the proportion that are prophylactic and the degree of polarization. And the rate of adoption of prophylaxis can be too fast, ultimately making the epidemic worse, or too slow, meaning it happens behind the epidemic wave and is just simply not doing anything at all. So we have a number of complex interactions that are clearly showing up even in this simple model, coupling opinion dynamics and disease dynamics. Now with COVID here, this has become that much more relevant, and we can actually get some data on behavior. In particular, this is a site we found that's tracking face mask wearing in public places. It comes out of the UK, but they've got data from several different countries. And so we're hoping that we can use this kind of information to try and get at least some sense of what the values of those behavior change rates might be in our model. Okay, and I think I better wrap up there because we're almost at an hour. Thank you.
Thank you so much, Professor Tyson. What a great talk. And even though we started...
Thank you.
Thank you. Let's start with Professor Tyson.
Yeah,
I love that. Thank you so much. Thanks a lot. Even though we started some few minutes late because this was the first second series lecture, you were able to keep to time, and I really appreciate that. And this topic is really very important. I'm glad we had this at this point given that we have, when it comes to COVID, like you rightly mentioned there, an opinion, and I'm glad we have a lot of our students and students all around the world watching this to think out of the box and see how this type of topics can be used to actually find out how the opinion dynamics when that people had towards quarantine or social distancing can drive the second wave of COVID-19 that we'll be having. So this is a very timely topic, not just timely for our COVID elections in the US. Our next door neighbors will be having the elections. How will people influence others' opinions? So this is a very timely topic for students to react on. And I will not emphasize more on this. I will allow other people to ask questions or to react to this. And we have a lot of our students here. Before I
Jude,
give the room, yes.
Someone's just turned a vacuum on upstairs. I'm going to run up and tell them to turn it off, and I'll be right back.
Thank you so much.
Okay, sorry.
Thank you so much. Thank you so much. Before Rebecca comes back, guys, please think about your questions. This is a very timely topic. Think in line with elections. Think in line with our COVID, opinions about quarantine, how that affected the dynamics, and look in line with what she has. She had a voter model. She started with a voter model and then moved on to look at coupling two layers where you have the opinion layer and a disease layer. How you couple that and that influence the dynamics of the disease. How that can influence voters' decision. So think in line with
I'm back. Sorry.
Thank you so much for coming back. Yeah. I was going to say, let's clap for Professor Tyson again, because she did a great job. And then please, we have room for questions. Feel free to ask your question here. If you want to come online and ask a question, we will welcome it. And we'll love students to come online and ask their questions directly.
Yeah, Jude, there is a question from Rob Davis. He's asking if you can turn the video and voice on. So please, Rob Davis, yeah, you can ask the question now.
Hello, thank you. That was a really fascinating talk. It's also very far from my own mathematical knowledge base. So I have a question and a follow-up, and I apologize if they're both kind of silly. But if I'm understanding the model correctly, you had interactions between people with maybe distinct but similar attitudes, so maybe a +1 and a +2, and a +1 and a -1. But I don't believe I saw much interaction modeled there where maybe two people are at the extremes.
Right.
And so okay, so I'm glad that you said that, because that signals that my understanding is not too off base. And so I was just wondering if that was deliberate, and maybe your reasoning why. Maybe that kind of influence is negligible, or what it was. Because I think with something like, and I don't know for sure, but my gut says something like modeling spreads of disease and those attitudes is going to be different than modeling opinions on political issues.
Right. So actually, I'm trying to. Okay, wait. Actually, those extreme interactions did happen. So my arrows are not good, right? Actually, they do interact with all the opinions. So here, if I'm looking at the ODE, so if a -2 interacts, so the problem is I've got these 1 minuses, which, because you can say, okay, all the other interactions are going to involve this. This is where you get the 1 minuses. But if a -2 interacts with a +2, then the -2 will move to -1. It becomes a plus, because you just move 1 step closer to the opinion on the other side.
So you're not
now how?
Sorry, I was just making sure I'm understanding. You're not assuming that someone is going to go from a +2 and say, "Oh, you've completely changed my outlook radically, and now I'm a -2," or something like this.
Exactly.
Okay.
It's always 1 step at a time. So that would be a different model if you allowed jumping.
Okay. Thank you.
Okay.
Thank you so much, Rob. Elena?
Yeah, so there is another question by Rinel. Sorry, I'm not sure if I'm pronouncing your name correctly.
Yeah,
you can come on video and ask your questions now.
Thank you. Thank you. Yes, it was indeed Rinel, the pronunciation, so it was right. I want to thank the speaker for the interesting talk. I really liked the idea. When I saw the title, I was not sure of what I would hear, and I really liked it. So, yeah. So I have two questions, basically. Like I have a lot of questions comes to my mind, but two seems to be very interesting. The first question is really like, with some friends, we did a handy model in which we incorporated in an epidemiologic model some behavioral models. So the main idea was like, well, we have to give medication to these people, but then they don't want the medication. And we model like the fraction of people who will say like, we don't like your medication. And there was what appeared in that model is that there was a fraction of the amount of people in the population, which when they said no, it was worthless to continue the epidemics efforts. Because if you continue pushing for this effort, then you are just wasting your time. Is this something that appears with this parameter? Is there a threshold in polarization in which one can say, okay, well, after such a level, it is efficient. It's like essentially worthless to push the efforts in this direction. Maybe we should just stop. So this is one question. The last question, the second question, so that I don't keep the floor, is an agent-based model. In general, I always have a question: is does it depend on the amount of agents? Like, if I guess you did this with a fixed number of agents. Like, if I have like many more, does the behavior stays like it is, or is there a transient thing? Is there ergodicity when I get the large population size, or does it get all fuzzy and it's not interesting? Thank you.
So that second question is easier to answer. So I'll do that first. Yeah, we did look at grids of different sizes. Now we always had a square lattice. So if you have a different shape, then I don't know the answer. But on a square lattice, the results are the same, no matter what the size is. Of course, what changes is how long it takes to get consensus. Okay. That can vary a lot. And then, of course, if you change the size of that spectrum, so the larger the spread, so if opinions can go from -2 to +2 versus if they can go from -5 to +5, then it takes longer. So now to get from one side to the other takes a lot more steps than it does from -2 to +2. So those affect the time scale, but they don't affect the behavior, the patterns of behavior. Your other question is quite interesting. That's asking for how much, I think, if I understood you correctly, you're asking how much bang you get for your buck by introducing more polarization or more prophylaxis. And introducing more, you can think about it in two ways. You can think about, well, if you're able to fix it. So, I mean, the government, when it imposed a lockdown, was able to fix a certain amount of prophylaxis. And that was, of course, very effective, but very expensive. Now it's a little more loose. It's recommendations. It's please stay home, please be careful. And it's more about how quickly individuals respond to rising cases. And there, yeah, you don't want the response to be too fast or too slow, because you can get these counterintuitive effects happening. So I'm not surprised you found that, but it is interesting. And then in the economics model, which I didn't have time to talk about, that's also related. How much bang do you get for your buck? And it turns out that if you try to bring deaths down to zero, if that's your focus, your costs go through the roof, but you don't really reduce mortality all that much.
Thank you. Thank you so much.
You're welcome.
Yeah.
Thank you, Renee, for the question, and thank you, Professor Tyson. We still have room for one or two questions.
Yeah, we have a question by, so Alisa wants to ask a question. If you want to, yeah, here we go.
Hi, I'm not sure if this was covered or not because I'm not an expert in this area, but from what I understood, you were saying in the model, if you have two people who agree with each other, then there's going to be some kind of amplification of their opinion, right? And if you had two people who disagree with each other, then they would move towards one another. This is the idea. So what you've been noticing, sorry, go ahead. I want to make sure I...
Well, they're slightly separate processes. So if you have a +1 interacting with a +2, then the +1 would move towards the +2. If the +1 interacts with a -1, it'll move towards the -1. So those are just simply moving towards whoever you're speaking with. The amplification is this separate process where a +1 with a +1, for example, they would, let's see, so if it's a +2 interacting with a +1, instead of moving toward the +1, it becomes a +3.
Oh, okay, okay, I see what you're saying. Yeah.
It's the echo chamber thing, right?
Yeah, so that's the thing that I'm seeing, that you have this idea that there's this echo chamber, and it seems that actually kind of reflects reality. So I have this question, do you guys model what happens, so you notice this online, when people who have very extreme different opinions talk to each other, instead of becoming closer together, they become more entrenched in what they're thinking, like almost that they would be pushed further apart. Like, is that something that anybody's looked at or tried to model in these kinds of opinion things, or no? Uh-oh, I'm gone.
No, we can hear you. Yep.
Oh, okay. Everything's just frozen, so I wasn't sure.
No, we can hear you. Professor Tyson, I think she's...
Maybe she froze.
There she froze.
Nuts.
I think she froze. Let's see if she'll come back. She should be able to come back. Okay, she will be rejoining, I hope so. So hopefully she join. And again, before she joins, I just want to emphasize how important this topic was and the opinion. And at York University, there are a couple of people working on this type of opinion. If you are based at York, there's Ian Moyes, myself, Jen Heffernan, working on these type of opinion models, looking at how, basically look at how opinions between quarantine, people who were pro-quarantine and those who were against it would drive the dynamics in the second wave. So people are working on this at York University. If you're based at York, okay, Professor Tyson is here.
Sorry about that. That was an excellent question, and I don't know if people have looked at that, but it would certainly be worth looking into. There are a lot of behaviors like that that would be interesting to add to the model. I don't know how much of those other behaviors one needs. So if you want to predict exactly how long it's going to take or what dynamics are going to look like, we might need other, there are other behaviors that we want to include. But I think there'll be a real temptation to add every behavior out there that we can think of. And not all of them are going to be useful in terms of giving us more understanding of the system. But absolutely, I think that's a very interesting one. Sorry, Jude.
No, thank you, Professor. So because we started late, we're just begging, so this will not always go beyond 1:30, but we'll just take one question, one additional question, and then we'll end there. Again, the reason why we're going above what 11:30 is today is because we started pretty late. So Elena?
Yeah, sure. There is a question by Shaoli. I'm not sure if wants to ask in person or not, but I can read the question in the meantime. How to model the influence of opinion leaders?
Leaders. Oh, that's interesting. So there's all this work done with Cousins and Levin and other people looking at leaders and followers and how many leaders it takes to get the population to split and things like that. Yeah, that's very interesting work. We haven't thought about that. We have thought about including stubborn individuals. So individuals who absolutely do not change their opinion. And these, I think, would be equivalent to leaders. And so certainly work by these other people has shown that it doesn't take very many leaders to start splitting a population. And so it probably wouldn't take very many stubborn individuals to to create the polarization. So it could happen even faster, but I haven't looked at that yet. We've been talking about it for a long time, and the trick is how to implement it. It sounds easy, but it's actually trickier than it sounds.
Okay, thank you so much, Professor Tyson. At this point, we will come to an end. And before we end, I really want us to thank Professor Tyson again for a great talk that is very timely. We really appreciate this because we all need this for COVID, for elections that's coming up. Thank you so much, Professor Tyson.
Thank you. It was a pleasure.
So going forward, we'll continue with this,
you.
and you'll be hearing from us subsequently. Again, thank you so much for attending this, and we hope to see you next time in 2 weeks. Thanks a lot.
Thank you. Bye.
Bye, everyone.
Bye-bye.